All right, in this video, we're going to go on to our third main type of isometries, a reflection. And a reflection about a line M is a transformation which maps a preimage point A to an image point A prime such that the line segment A to A prime is perpendicularly bisected by the mirror line M. The given line M is called the mirror line or axis of reflection. The reflection is denoted as capital M sub whatever the mirror line is, little m. So a reflection, maybe informally called a flip or a mirror, about a given line is formed by moving each point of the preimage across the given line to its corresponding image point, which will be the same distance on the other side of the line. The line segments connecting the corresponding preimage and image points are all perpendicularly bisected by the given line. Notice that we use a M mirror for a reflection since we reserve R for rotation. Okay, and let's take a look right away at that in GeoGebra. So here we're looking at reflections. Here we have a preimage. Now, by the way, remember to talk about a particular um, transformation, we have to specify the defining parameters. Like for a translation, we had to specify which vector we were translating by. And for a rotation, we had to specify the center point and the angle. For reflection, we have to specify where the mirror line is. So let's just make a mirror line here. And we can have a command in uh, GeoGebra here where you can say reflect about a line. So we can take this point here, reflect it about this line to get its image point. I think it made it. It's just off screen here. There it is. Okay, and I think we can do the same for B. We might be able to do multiple ones at once. Let's see. No, it's not doing it. Okay, so let's do it this way. Reflect about the line. Select all of these points. And select then the line here. Yep, that did it. Notice that F and F prime are here. I moved that. Let me just get rid of F, so that should get rid of F prime. I don't need this. If you notice that D and D prime are the same, points on the mirror line are fixed. Okay, and then these points here, let me go ahead and follow my standard convention of making the image red. We have that. Again, we've got more than one copy of some of the vertices, so I'm just going to get rid of the extra copies, or at least not show them anyway. So the images are of A is A prime, image of B is B prime, image of C is C prime, and so forth. Now, that's what we get for a mirror image. Notice there's no way to get this to just slide it over there on top of that one or rotate it to there. It's going to be oriented opposite way. So this is going to be a reflection involved. Notice that if you have points on the line, they are fixed. So those things here, so we can have the line going through the figure. It can be down here, it could be here. We can change the figure and we can see that rotation continuing. So if you're going to do anything with these, you might notice that. These are fixed points there. Now, geometrically, what does it mean for it to be rotated? It means if you connect up a pre-image and an image point here, that the midpoint of that line segment is going to be on the mirror line for starters. And if you find the angle that it makes there, it's going to be a right angle. Okay. So the line connecting the pre-image to the image is perpendicularly bisected by the mirror line. Okay. And it doesn't just happen there, it happens at every single point along the way here if we have it like that. Okay. So that, again, the midpoints of all of these things are the same, and the angles are all right angles. So every one of these right here is actually a right angle. Oops, thought I had these selected. Okay, and it doesn't matter where these are, where these go, that stays the midpoint and the right and that there. And we could even do that with a point on the original here. I can take that guy and reflect it about this line. And again, if we connect those up and find the midpoint of that, it will be on the line. And if we compute the angle measure, it will be 90 degrees or pi radians. I'm not sure if I grabbed the right point there, so let me fix this. There we go. Sure enough, right angle. Doesn't matter where we are there. So that works. If the point's on this side of the line, the pre-image point, the image will be on the other side. The point's on this side of the line, the pre-image is going to be on that side. If the point's on the line, it will be fixed. It will be the same pre-image and image point, fixed point. Okay, so that is the idea of a reflection in GeoGebra. Now, one thing that's kind of interesting is a reflection even a congruence mapping or not? Okay, so if we look back here and just look at the image of the red and the blue triangles, there's no way, if this was a physical triangle, maybe it had its interior there and you could cut it out, and it was laying down on the table in the plane, how could you get it to be on top of this one? Well, you couldn't get it there if you weren't allowed to lift it off the table. So you could get it there by rotation or reflection, or rotation or translation if that was enough. But in this case, that's not enough. You couldn't get it there. So if we were living in 2D space like Flatland, like Flatlanders in the novel Flatland, we wouldn't be able to we might not think of this as a congruence mapping because we couldn't physically turn one into the other. Okay. Here's an analogous question for us 3D space dwellers. Is a left shoe congruent to a right shoe? Or how about a left glove to a right glove? We might not think so, since to transform one into the other, it would take access to a physical fourth dimension to flip a left shoe to turn it into a right shoe and vice versa. Similarly, a 2D reflection requires accessing one higher dimension to physically perform it. On the other hand, so therefore this is a reasonable argument to exclude reflections as congruence mappings. On the other hand, if we want triangles with corresponding congruent parts to be congruent, then we have to include reflections as congruent mappings. Furthermore, reflections are definitely isometries since they map line segments to congruent line segments. And we want all isometries to be congruence mappings. So for these reasons and a few others, it's advantageous for us to include reflections as congruence mappings. They will certainly map a triangle to congruent triangle or a line segment to a congruent line segment and so forth in that same plane. Now, as is typically the case, we will consider reflections to be isometries and congruence mappings like pretty much everybody does. But I did want to point out that there is something a little different going on with reflections than the other two in some sense. Next, we can talk about doing compass and straight edge constructions. The next video is going to go into that a little bit more. And so the basic idea is to make a point. Let's just see, how do we get A to A prime? Maybe we'll just do it real fast over here. Okay, so let me delete a bunch of stuff here. Oops, that's no good. I got rid of the mirror line. Okay, so what if we just want to get A to A prime over here? Okay, well, what we want, once again, is we want this line segment here to be a perpendicularly bisected by the mirror line. Well, what do you know about things that will give you perpendicular bisectors? Well, that's one of the properties that we get from a kite, or especially a rhombus. So if we could just make a rhombus here, we could make this work. So what you can do here is take, we're starting with the point A, suppose you don't have anything else. So we just go out here to some point on the circle, and then we want to make, actually I can do it this way, it's kind of cool. Okay, so I can do that. I can use my compass tool, which is just going to set it at the same length as this circle, and I want to put it where this other point meets and where this one meets. Okay, so actually I probably could have just started this way. Let me restart it. So what you can do is just pick any point that you want here and make your circle going from there to A. Then find where it crosses here and make a circle going from, let's see, then you want to make a circle going from, let's see, here to here, and then from here back to A. So if you look at the way this is set up, all those circles have the same radius. So that means that this shape right here has to be a rhombus. Maybe I'll make it a different color so we can see what we're talking about. So this right here, by the way we set it up, since all those circles have the same radius, that right there, that orange thing has to be a rhombus. Well, what do we know about a rhombus? The diagonals are perpendicular bisectors of each other. And so we can, by making a rhombus that way, we can make this point here. And I didn't use anything except for what you can do with an actual physical compass there. Okay, so that's the way you can construct that. We'll hit this again using Geometry Sketchpad in the next video. So your exercise is to take maybe a triangle like this, draw a scalene triangle, draw a line segment maybe through it or beside it, and make that. So which points are fixed? What can you say about the position of the points in its image point? We can do reflections by folding, tracing, and using a mirror or a georeflector. For folding, we can fold the paper along the line of reflection, trace the original figure on the back side of the paper, open the paper, and then trace your trace. And for example, this works for patty paper. As you can see through, it works really well. For tracing, use transparent or translucent paper. Again, patty paper is really good. Trace the original figure in the line of reflection. Mark a point on the line of reflection with a dot. Now simply hold the 2 points on the line of reflection and flip your trace over so that the line of reflection and the marked point on the line stay the same. Okay. You can use that as a check. And there's a device like this called a mirror or georeflector. It has a little beveled edge that you can put down here at the bottom with the bevel part facing you. Put it on the line of reflection and you can see through it and see this on the other side. There is actually not physically anything drawn over here on this side of the paper. This is just what you see when you look through it. So you can reach through with your pencil and maybe mark some key points there and use your straight edge then to finish up the image if you want to draw an image like that. Here's a little video. This is the image source where I got this, and here's a video on YouTube with somebody showing you how to use that. Here are the steps again in GeoGebra. There are some additional reflect transformation commands in GeoGebra. Reflect about a point, reflect about a circle. These are not reflections. These are something else. So I'm going to leave those out of this video.